Hello everyone, and today we're going to be talking about the physics of sound waves. So up to this point, we've kind of introduced waves, we've talked about some of the structures, and we've briefly talked about some of the types, specifically mechanical waves. So let's take a quick look before I jump into more specifics of sound waves, where we're at on our graphic. So if we look at just waves, we spent a lot of our last lesson talking about mechanical waves. And now today we're going to focus in and we're going to really talk about our longitudinal waves. So we're really just talking about this section over here on our table. Because our longitudinal waves, they're going to be our sound waves. And so we're going to spend some time specifically talking about sound waves. So to start that, let's just talk about, well, what is sound? Well, how does sound form? So sound is a form of energy caused by vibrations of matter, and it's always a longitudinal wave. Which, remember, as that reminder, those longitudinal waves are those that have direction, their wave travels in the same direction of those vibrations. And so, again, what that means is if we have our wave traveling this direction, then that means the vibrations are also traveling in that same direction. So they're moving together. We don't have that up and down motion we frequently see in transverse waves. It's running in parallel with each other. Okay, it's almost like bumper cars. If you think of the air molecules that's traveling through, one hits and then it gets bumped, right? And we have these compressions and we have these rarefactions attached to it. Now, with sound waves, it must travel through some medium because it's a mechanical wave, which means if there isn't matter, if there isn't that medium for it to travel through, that wave can't go anywhere, which is why in empty space, sound doesn't travel. All right. And so that's what most space science fiction movies and all that get wrong, in which there's all these glamorous explosions and noises in space. There really wouldn't be. Second, well, right? So that vacuum, that idea in space, right? There is no sound in outer space. So I kind of just touched on that. So, moving on. So our frequency and volume of sound. So what this means, so the general range of human hearing is from 20 to 20,000 hertz. So that's our frequency, if you recall. We use hertz to abbreviate that. And to kind of reference, so we think of, okay, so how do we perceive this? How do we hear? The higher the frequency, the higher the pitch, the higher that note, right? The higher that tone. So it's really, really high. The lower the frequency, the lower the pitch, the lower the note. So, right? So someone who has a very low voice, they're going to have a much lower frequency as their standard talking voice, whereas a higher frequency is going to be those that typically have a higher speaking voice, for example. And now we can measure volume of sound by using decibels. And so that's how we record the volume of a sound. And now when we're looking at the volume, the decibels connect to the amplitude of the wave. It's not a direct relationship. So what this means is we can't just say X amplitude of a wave would equal this. Decibel is actually like a scale that adjusts everything. It's a logarithmic function. We're not going to get into all of those details for it, but just know that a small change in a decibel number is actually a big difference in the amount of impact. So you could go from having really very little, no damage at 50 decibels to severe damage at 70 or 80, which doesn't sound like a big change, but it's a really significant change in the overall volume of that wave, sound wave. So the threshold for hearing is 0 decibels. So that's the softest sound a human ear can hear. That's like, we're talking super, I mean, you may not even notice it. And then it's almost just general random noise. Sometimes you don't realize how much background noise there is until it's gone. Right? If you ever taken like a really far camping trip or somewhere more remote, you realize how truly quiet it is when you don't have just like the noise of cars and other things just very distant even in the background. Or even you may notice things seeming louder at nights or in the morning because there is less of that just general noise pollution is kind of one way to say it. The threshold for pain is 120 decibels. So this causes actual physical pain, which it's so loud, right? That start could be really loud, and now your ears just hurt really bad. Or you accidentally have your headphones on full blast when you turn them on, plugged into your phone or whatever. And that actually hurts, right? You're like, and you almost need a sensory break from all that noise because your body is just overwhelmed from it. It can actually cause that. Anything over 180 decibels can cause brain damage and actually kill you because it'll rupture blood vessels and things like that, and absolutely will cause deafness. Even 120 decibels over a sustained amount of time will cause that to occur. So what I just want you to do is just take a second, pause this video, and kind of do a little self-survey for yourself just to kind of get an idea of, do you have healthy listening habits or not to various things or your exposure. So think about the number of hours per week you listen to earbuds at high, volume. So that's typically 70% or more. That'll vary per device because some devices at 70% are much quieter than others, depending on how amplified that sound is, but effectively at a very high volume. The amount of hours a week you spend in a very loud conversation. Now, when I'm saying loud conversation, I'm saying like you are not just talking loudly, you're basically like shouting. Okay, we're not just, for example, if I'm teaching to you in person, if that's happening and I'm using like a speaking voice, that wouldn't be a loud conversation. We're talking like you are screaming, right? Very, very loud. Okay, so a good example of this could be like at a sporting event. Now with COVID, of course, that's tougher, but a sporting event, if you think back to with when those are normal, with large crowds, that would be a good example of that. Hours per year you spend around loud machinery. So that could be sanders, motorcycles, a tractor, any sort of saws, things like that, lawnmowers. All right. And we're talking again, very close proximity. Okay. And then the hours per year you spend at a concert or sporting event. So that connects to that shouting. Those are similar levels, but concerts are typically louder because the music could be very, very loud and is very sustained. Okay. So let's take a second and answer those. So let's just look at some of those safe guidelines if we look. So of course being in the green is the best, right? And you'll notice there's a big jump between those, right? If you think of a normal conversation is at 60, and then like a food mixer or vacuum is 70. Okay, that's only a 10 decibel difference, but those are pretty big differences in noise. You think of a lot of vacuum is to a conversation. Actually, a lot of vacuums are getting quieter and quieter, but you think of just a standard vacuum. Car traffic's 85, and I think of like heavy city traffic, not necessarily like a couple cars passing on the road, right? That's what that's referencing. And you'll notice we start to kind of get in that yellowish area. And you can see now it says that threshold before permanent ear damage, actually. Now we're not talking like you're instantly going deaf, but what actually starts to slowly kind of your hearing will decay a little bit, and that's pretty normal through life. I'm not, if you notice some of those things, you're not going to suddenly just like lose all of your hearing. Don't worry, but it's something to be really aware of, which is why I'm talking about this. So for example, if you were to be going to a concert that's really loud and you are there for over 2 minutes, you're actually getting hearing damage. And like if I've gone to a concert, that's sometimes I have to leave because it's almost like I get tired, right? And you'll notice this too if you leave a loud event like a concert and things like that. If you've ever noticed, everything seems really kind of muted and deafened. Nothing seems as sharp. It's almost like, this sounds weird, but it's almost like when your eyes get tired, it gets blurry. It's like your hearing is blurry, and that's because it's just completely overwhelmed, and it is so oversensitized it can't process that. And that's actually a symptom that your hearing has actually taken some damage. All right, again, listening to your MP3 player, an iPod, or your music off your phone, or whatever listening device at extremely high, like max volume, absolutely that's going to cause a lot of pain and a lot of hearing damage for sure. If you think of like a firework going off right next to you, or a stereo on full blast, all those things, or you think of a jackhammer. Now, all of these things are without any sort of hearing protection. And that's why hearing protection is really, really important. Like, I'm not saying you can't go to concerts, but one really awesome thing that you can actually get, they have specialized earplugs. That what they do is they basically just like lower the volume of the concert. Because I don't know about you, but I find them excessively loud. Okay, and so what that does is it doesn't block out the noise. They're not like earplugs. It's literally a filter. And so what this does is it now allows all of the music to still go through and sounds, but it just softens them to a much more normal listening level, which is really cool. And so if you're someone who does go to a lot of concerts, I would recommend looking into those things to really just protect your hearing so you can always enjoy those concerts, right? There's reasons a lot of musicians that give a lot of concerts. I mean, now they'll have a lot of special, like they'll have those stage monitors because then that way they can hear how they're playing without it being super loud. And that also helps them protect their hearing as well to prevent hearing issues, which some artists do have later in their life. So the next thing I want to talk about after my little public service of keep your ears healthy. You guys know I do a lot of stuff with headphones and I want to maintain hearing, so I had to do that little piece, is speed in relation to sound. So the one thing we can talk about is supersonic. So if something's supersonic, it's faster than the speed of sound. All right. It depends on the altitude. So if we're at sea level, right, or you can kind of think ground level, things like that, it's about 767 miles per hour. If we're in the really high upper atmosphere, it's 660 miles per hour. So it actually gets lower, which is interesting, right? And if we're going at the speed of sound, that's known as Mach 1s. And so, we could go to Mach 2, Mach 3, right? It's just a multiplier. So like Mach 4 would be 4 times the speed of sound, if we're looking at that. And we'll talk about why, with those atmospheres, why we get this difference between the speeds of sound. That's something that we'll talk about, we'll kind of address in just a moment here. So if you're wondering, well, hey, why is it different? We'll talk about it. And then finally, if you're going really fast, it could generate a sonic boom. And this is an explosion of sound waves and air forced forward by a supersonic object. We talked about sound waves, the longitudinal waves, they have a compression. And what happens is when you go really fast, that compression gets really, really tight. And eventually, it's almost like it snaps the air. That's probably the simplest way that I can explain that. And that's what causes the sonic boom, which is basically like a small explosion, which is why planes that travel that fast, they can't fly super low to the ground, because they could do that. They could shatter windows and just cause general disturbances. And so that's why there's air ordinances preventing flying at certain heights and altitudes and speeds at different areas. A lot of high-tech planes, especially in the military, they're being designed to prevent the sonic boom by certain shapes that allow them to kind of pierce through that barrier that's created that compression. Maybe it still generates it, but it's not as big of an explosion. And then if we have subsonic, that's slower than the speed of the sound. And this is me being really funny, thinking of, an elderly person driving, they always had the bad rap of driving very slow. And that, of course, that's subsonic being anything that's lower than the speed of sound. And of course, that threshold does kind of change too, depending on our altitude, right? So this is the piece that kind of connects to the speed of sound with different stiffnesses and densities. So we have two things. Now, this video, I'm not going to play here within this. I'm going to actually have it linked in our Edpuzzle lesson. So that's going to pop up. I'll have right around this moment. It'll pause, and it's going to show you that link so you guys can watch it. Now, the stiffness is the property of material in which how rigid and difficult it is to bend. So something's really stiff. You think like a steel rod is really stiff because you can't bend it. It's not very flexible. It's very rigid. All right, it really, really holds its shape. Okay, it doesn't change its shape easily. Very strong. Density is that amount of matter in a given amount of space. So it's the amount of volume. So how tightly packed it is. Because some things can be really dense, but actually have a really low stiffness. And that would be a good example. That would be like gold. That precious metal is actually extremely dense. It's very, very heavy per amount of space that it takes up, but it's actually pretty soft, so it can dent really easily. Whereas steel is also fairly dense, not as dense, but it's extremely stiff, which is why we use it for a lot of structures, because it's very strong. Okay, and now basically the highlight of this video that I'll have linked for you to watch, I have linked, is the stiffness is by far the most important thing. So if something is extremely stiff, it carries sound much faster, and it tends to override the density. So density slows it down, stiffness speeds it up, is what's happening. But if something is really stiff, like a steel rod, it travels very, very fast. And that's actually why a lot of times when there's railroads being created, and before, modern communication, they could actually communicate by tapping on the metal, and they could that sound could travel much faster than if they were shouting to them. And so they could have different taps for meaning 2 taps for this, 3 taps, whatever it might be. And it's something like 14 times or much higher, that it can actually travel. So stiffness pretty much always overrides the density piece of it. Well, the density could slow it down because there's more things it has to go through. It's like a crowd you're trying to get through. If it's really stiff, it allows that energy to be more efficiently passed on to the next one. And that is the last piece I wanted to talk about with sound. If you do have questions about this, absolutely let me know. And then we'll continue on with our next lesson later. Thanks for watching.